Welcome to my course on thermochemical processing of materials. My goal is to teach you how to make great materials. Let's start this lecture. In this lecture, I'm going to teach you about mixing thermodynamics. And the idea behind this lecture is that if I have an alloy, and the alloy has, say, a number of chemical components or chemical elements or chemical species, all of these words are equivalent. Suppose that the alloy has a number of chemical elements, iron, copper, tungsten, and so forth, and you are casting this alloy by solidification. And you ask yourself, during this casting process, what are the concentrations of each one of these elements in the liquid state, and what are the concentrations of all of these elements in the solid phase? That's a very important question because it will you can control the mechanical properties, thermochemical properties, physical properties of the cast alloy if you know the composition and how it varies in space as you are casting the component. Another example, if you're doing chemical vapor deposition, and in chemical vapor deposition you have vapor and solid, for example. You have some kind of equilibrium between these two, or vapor and liquid in some cases, and you want to control the compositions in the mix of gases and the mix in the liquids. So the question is that how do you do that? So we're going to now, the title of this lecture is Mixing Thermodynamics, and we will basically cover in the first part of the lecture the ideal case, which is Raoult's law, and then later on we will look at a variation in which non-ideal behavior is brought into bear. So the lecture here is a material processing, and the title is Chemical Mixing Thermodynamics. So we're going to start by looking at the vapor-liquid equilibrium and Raoult's law. And when you see here, the first step is to equate the chemical potentials in the vapor phase and the liquid phase, because that's the expression for equilibrium. And we do the equation here for a number of species, I equals 1, 2, up to n. So a species I is like iron, tungsten, copper, etc. That's what we mean by a species. And V is a vapor phase and L is a liquid phase. So what we will do is we will have to basically calculate the chemical potential in the vapor phase and calculate the chemical potential in the liquid phase and equate them and get an expression for equilibrium that hopefully can answer that question. How are they going to split? So in order for us to find that question, we will look for the fractional concentrations in each phase. The molar fractional concentrations in the vapor phase, we're going to call it Y. And for each one of these species, it will have a subscript I. So Y sub I is the fractional molar concentration in the vapor phase. Now, if I say X sub I, it will be the fractional molar concentration in the liquid phase. So we're going to be hunting after those numbers. So in order for us to do that, we will have to find the chemical potentials. Now the question is, the chemical potential, where does it come from? Chemical potential is like the Gibbs free energy. But notice that in the previous lectures, we found that the chemical potential is essentially the Gibbs free energy of the pure state if the element is not mixed. But when we mix them together, we get an additional part due to the mixing. And that part is RT times the natural log of the fractional molar concentration. So that's our starting point. So I'm going to go back now and then follow on the screen the equations by equating the chemical potential. We'll talk about it, and then you will see me working out on an example. So here I have the chemical potential is the Gibbs free energy of the ideal gas. It's a vapor state, so I'm going to say it's an ideal gas, plus RT ln of Yi due to the mixing, and this is the Gibbs free energy for the liquid state of element I, plus its corresponding contribution for the mixing, RT ln of Xi, and then we will take this term to the other side and this term to this side. Then we get RT ln of Y sub I over X sub I is equal to Gi in the liquid phase minus Gi in the ideal gas phase. And I'm going to use an approximation that it is an ideal gas. Notice that dG generally is equal to VdP minus SdT, and if I have an isothermal process, then this term drops out. So I have VdP, and for the ideal gas, V is equal to RT over P. So if I introduce that in here, I will get an equation by integrating the left-hand side between two limits, the P and the Pi sat, and the right-hand side between the two limits, P and Pi sat. I get the ratio of the natural logs. And I'm going to make another approximation now for the liquid phase, and this approximation is that its Gibbs free energy is independent of the pressure. So if you evaluate it at Pi sat or at P, you get the same result. Does anybody know why is that true? If we have I wanted just to say that this is an approximation, of course, and we know that dG is equal to VdP. So if you want to get the change in the Gibbs free energy between two different pressures, say from P sat to P, then you should integrate it, right? Like what we did for the ideal gas. But here for the liquid, we're going to assume it's independent of pressure. Well, this assumption corresponds to incompressibility, that pressure doesn't really make the volume change, and therefore we can pretty much ignore it. So we'll just assume that for the moment so that we can derive Raoult's law, and then later on we will see how we would make correction for that. So let's continue on, and with that, with this assumption, then we will now see that on the left side we have RT natural log of Yi over Xi, and on the right hand side we get the Gibbs free energy of the liquid at Pi sat and the Gibbs free energy of the vapor at Pi sat. And what we know from before in equilibrium, we notice that if we plot G versus, say, the pressure or the temperature at constant pressure, at constant temperature, if we plot it as a function of pressure, and you get a transition, say you plot this P for the liquid phase, and then you plot the G for the vapor phase, then you will see, or the green will be for the liquid phase, and the red would be for the vapor phase. So you'll find that at some critical pressure, let's say this is a saturation pressure where the transition happens, and this side, the Gibbs energy of the vapor phase is less than the liquid phase, and therefore you have vapor, and on this side the Gibbs energy for the liquid is less than for the vapor, so you have liquid. And exactly at the transition here, the Gibbs free energy for the liquid is equal to the Gibbs free energy for the vapor phase, and that is for the species. This is exactly what's happening here and therefore we can cancel these two terms together. Having said that, then you will reach this form of Raoult's law, that the product of y sub I times p is equal to x sub I times pi sat. This product is essentially the partial pressure of element or species I in the vapor phase. And this side here, this is the product of the partial molar fraction of species I in the liquid phase times its corresponding saturation pressure. So that is what we will have in here, and we can now assert that this is a statement, appropriate statement of Raoult's law that we're going to use. So this we will now summarize. The Raoult's law tells us that the partial pressure of element or species I in the vapor phase must be equal to its partial molar fractional concentration times its saturation pressure in the liquid phase. Let's now take two things. Now in the remaining part of the lecture, I'm going to take two things. First, I'm going to derive Raoult's law again from scratch, but not assume that the Gibbs free energy of the liquid is independent of the pressure. So I'll take that assumption out and see what happens. And then second, I'm going to give you an example, numerical example of how you can compute the concentrations in liquid and vapor phase for a binary system that I will introduce to you in a minute. So let's first try to do the derivation of Raoult's law, enhance Raoult's law if you want, with the assumption removed that the liquid phase Gibbs free energy is independent of the pressure. So let's just go for it. And now this is the idea of the Poynting factor that I'll introduce. So let me just start the derivation here by saying that we start from mu I in the vapor phase is equal to mu I in the liquid phase, and that gives me each mu is its corresponding G, and G is when I take in the ideal gas plus RT ln of Yi. This additional part is for the mixing, and this is equal to the Gibbs free energy of the liquid phase in its pure state plus the RT ln of Xi, which is the additions due to the mixing. And when I take this term to the other side and rearrange, I get RT ln of Yi over Xi is equal to the difference in the liquid at P minus the Gi of the vapor at P. Notice that I put it at P, and I know it's a function of temperature, but I'm holding the temperature to be constant. So my job is to find that difference at P. So to get at it, I'm going to do two steps. This one on this side and this one on this side. So this one on this side, I do integrate. I know that dg, so take this here on the side, dg of I is equal to VdP. That's my starting point. So I have to integrate this for the vapor and the same for the liquid. So for the vapor, we did it before, and that gives me Gi ideal gas at P minus Gi ideal gas at Pi sat. That difference that's the difference on the left side, is equal to the integration of the right hand side, which is now RT ln of P over Pi sat. So right now I was able to get the GI vapor at P. If I wanted, then I can use this expression. So on the left side, if I do the integrate on this here, if I do the integration, I get V times P minus Pi sat, because I am holding the volume to be a constant, and this should be the difference between GI of the liquid at P minus GI of the liquid at P sat. So on the left hand side I have this difference here. So this is GI of the liquid minus GI of the liquid at P sat is equal to V times P minus Pi sat. On the right hand side I have the difference between GI of the vapor at P minus GI of the vapor at P sat. If I subtract the term in blue minus the term in blue, this will be equal to the difference between these two. Then I come up with this solution. So let me just clear the page, and then I'll have now the solution that you'll see. So in here I have the result is that I have now RT ln of yi over xi, which is equal to GI liquid minus GI ideal gas. That difference now I can find it from the previous page, and that difference comes to be two parts. One is like what we did before, ln of Pi sat over P, and now we find that we have a contribution from the liquid, which is P minus Pi sat times V. And now if I take the exponential of both sides, then I get the solution that yi times P is equal to xi times Pi sat as before, times an exponential times V of P minus Pi sat, all of this divided by RT. So with that, we have an expression that pretty much modified Raoult's law and told us that now the partial pressure of species I, which is this term on the left hand side, P sub I, is equal to, it is true that is equal to xi times Pi sat, but you have a factor here, and this factor is called the Poynting factor. So we have now a new factor in the exponential that we can estimate if we know the pressure and the saturation pressure of each species. So it turns out to be that each one of the species will have its own Poynting factor that you can compute, and then you can now modify the set of equations that we derived before that represent Raoult's law. So in this case now I'm ready to do calculations that allow me to determine the concentrations of each chemical species in the liquid versus the vapor, for example. So let me take a specific example so we are able to see how the calculations proceed. What are we looking for? We're looking for concentrations. Let me just state a problem. I have two species, say acetonitrite and nitromethane. So two. These two species will exist either in the liquid phase or in the vapor phase. Okay? So if they exist in the vapor phase, they will have fractional concentrations, molar fractional concentrations. Y sub 1 and y sub 2. So I have two unknowns. Well, they're not totally independent unknowns because y sub 1 plus y sub 2 should be equal to 1. And then in addition to this, I have the same two species will exist in the liquid phase. And they have fractional molar concentrations. And those are going to be denoted by x sub 1 and x sub 2. And again, the sum x sub 1 plus x sub 2 must be equal to 1. So given that we know a pressure, any given pressure, and given that we know their saturation pressures independently in their pure state, unmixed state, the question is, what are their fractional concentrations in the mix? So I'm going to work on this example and see what we come up with in this case. So in this case, let's see. We have the example worked out here. So in this example, I have two species, and the two species are the acetonitrite, number 1, and nitromethane, number 2. And we have the vapor pressures are given by the Antoine equations. And the Antoine equations are just a small modification of the equation that we got from Clausius-Clapeyron, if you remember that before. So here, knowing the temperature, which is given here, I can plug in the temperature here. For example, if this is 75 degrees C, I plug it in here, and I get a corresponding saturation pressure for species 1P 1 sat. And again, knowing the temperature here, I can get P2 sat. Therefore, what's asked from us is to prepare a graph for the phase diagram of P versus X1 and P versus Y1 at 75 degrees centigrade. So the solution, first thing is that I find P1 sat equals 83.2 and P2 sat is equal to 42 kilopascal. And now I apply Raoult's law without the Poynting factor. I have two equations. Y1 times P equals X1 times P1 sat. Y2 times P equals X2 times P2 sat. What do I know so far? I know these two, and I can input any pressure I want. So if I input any pressure I want here as a known, then I have four unknowns: X1, X2, Y1, Y2. However, I have only two equations, equation 1, equation 2. How do I solve? How do I solve for four unknowns if I have only two equations? Well, I have to use this constraint that y1 plus y2 equals 1, and this constraint x1 plus x2 equals 1. I can use them directly by eliminating 2 out of 4, or I can just add the left-hand side to the left-hand side. When you add the left-hand side to the left-hand side, you get P, and the right-hand side to the right-hand side, you will get the x1 and x2. Remove x2, write it as 1 minus x1. Then now you get a final equation that is actually given here, and this final equation is P is equal to P2 sat plus P1 sat minus P2 sat times x1. So this is an equation for the relationship between the pressure, any pressure you choose, you plug it in, you will find the concentration x1. That's what it says. And it's a linear relationship. Give me a concentration, I give you a pressure. Give me a pressure, I give you a concentration. So that's X means liquid. So this is the line, the liquidus line. So this is the line on the liquid side, and it turned out to be a straight line. If I want to find the corresponding value of Y1, the same one is acetonitrite. So I want to find Y1, what do? I have to go back to Raoult's equation and substitute for what I know. Given that I know X1, then I'll find P. And given that I know P and X1, I can substitute and find Y1 and proceed. So having done that, then we see that we get For example, if you have at x1 is equal to, we can take just a specific point, for example, x1 equals 0.6. You find the corresponding pressure. It turns out to be 66.72, and therefore you can find the corresponding y1, which turned out to be approximately 0.75. So having done that, we are able to now have a plot of the pressure in kilopascal versus the fractional concentrations on this side. This is either x1 or y1. This line here, the horizontal, is either x1 or y1. So, for example, the relationship that we found in here is a relationship between the pressure and the corresponding x1, and it's a straight line. As you can see, the blue here is a straight line. If you find the corresponding relationship between P and y1, is not going to be a straight line and is going to be a green curve like that. And this green curve is supposed to be a green curve, and I'm going to draw it again here. So I have it here. It will be following this line, green curve here. So if we do a process, for example, I have at concentration x1 is equal to 0.6, and I'm reducing the pressure. When I get to point B at this point, there's going to be a start forming some vapor, and the concentration of y1 in the vapor phase is now this 0.7483. That's what we solved for. However, the amount of vapor is going to be very infinitesimal, like a bubble. So we call this point here the bubble point. So this is the bubble point. And as we reduce the pressure, then you get equilibrium between the liquid phase on the one side and the vapor phase on one side. So you move down this line for the liquid, you move down this line for the vapor phase until you reach this point here, and this is called the dew point. So these are kind of terminologies that people use to explain the equilibrium between the phases. So in essence, we have now learned Raoult's law, the ideal nature of the ideal gas law that we introduced to solve for the integration on dG and equated at the saturation pressure. And then what we've done for the liquid phase, we've done two steps. If we assume that it's independent of the pressure, then we get the original form of Raoult's law. If we now introduce it as we remove this assumption, we're going to have an additional factor that I'm going to explain to you in a minute. That's called the Poynting factor. So let's go back now and try to see how we're going to derive this Poynting factor, which is a slight modification of the original Raoult's law. So let's do that here by going into the Poynting factor, and I'm going to make that in here as actually we did this, but to emphasize it, is what we have here is the idea that the partial concentrations of the partial molar fractions are controlled now by essentially the equality of the partial pressures of each species in the vapor phase to the corresponding product of the partial molar concentration or fractional molar concentration times the saturation pressure and times this Poynting factor that you will have to evaluate when you do for each species. So I think we have now completed the story about how we're going to determine the fractional concentrations of each species in the various liquid phase or the vapor phase. Well, we haven't really reached our objectives. I mentioned in the beginning that we are trying to also, let's say, design a new alloy that can be cast. And in this case, I'm looking for equilibrium between liquid and solid. And we'll find that this type of equilibrium is not ideal, and we don't have the same kind of situation, but the principle is going to be very similar. And I'm going to leave it till next lecture when we will talk about the what I call non-ideal solutions. So I'll see you in the next lecture.